The mound and nest complex of Macrotermes michaelsoni is one of the most complex structures built by social insects, and its complex structure supports a complex function. The first step in teasing out this function is to understand the structure in all its complexity. Biologists traditionally approach structure through dissection. In the case of the termite mound, this means pick, shovel, and saw. This destroys much of the mound's fine structure, though, so an alternative method is needed. That method is endocasting. Endocasting involves filling the mound's internal network of tunnels with plaster of Paris and then washing away the soil matrix. This reveals the tunnel network's detailed structure. If this is done carefully, the remarkable complexity of the internal tunnel network emerges. This cast to the cap of a Macrotermes mound reveals the wonderfully complex structures that enable these mounds to capture wind energy in their special way. Rupert Soar of Loughborough University's Wolfson School of Engineering has taken this concept to the next level, endocast an entire mound. The concept is simplicity itself. Mix up 6 tons of plaster, fill the mound in stages, let the plaster harden for about 6 months, and then wash the soil away. It's a little harder than this, of course, and we had a lot of help from the staff at the Omacheni Agricultural Research Station in Namibia, where we work. This method reveals striking details of mound architecture. Seen in its entirety, the mound tunnel network emerges with an organic coherency that is truly stunning. There are the numerous surface conduits that run vertically up the mound and give rise to innumerable complexes of egress tunnels that enable termites to get to the surface to grow the mound. The egress tunnels also make the mound porous so that it can help the colony breathe. Deep within the mound is a reticulum of large tunnels that culminates in a large vertical chimney that extends down into the nest. Below the ground, the surface conduits merge into a complex subterranean reticulum that wraps around the nest. These passageways connect to the nest and allow termites to leave and roam through the network of underground foraging tunnels that radiate from the colony. A more detailed picture of the structure comes from a technique called slice and scan, developed by Rupert and his chief technician, John Webster. Here, a plaster-filled mound is sliced down by this machine. It consists of a cutting wheel mounted on a gantry that can position it precisely in the X, Y, and Z directions. The machine works like this. The cutting wheel shaves off a thin layer of the filled mound. After a little preparation to make the plaster stand out visually, what remains is a precisely cut face that shows the outlines of the tunnels and the mound. A camera mounted on the gantry then takes a photograph of the cut face. The cutting head is lowered by a millimeter, and the whole procedure is done again and again until the entire structure has been shaved down. The slicing of this mound took the better part of 2 months to complete. In this instance, the ground around the nest was excavated so that the nest could be sectioned too. When all the photographs are stacked and played as a movie, we get a CAT scan-like imagery that gives us a better feel for the complex structure of the mound's internal tunnel networks. Near the top, note how the egress tunnels seem to spray off from the large interior tunnels toward the mound surface. These large tunnels then branch and interweave to form the mound's reticulum. As we penetrate deeper into the mound, the surface conduits begin to array themselves regularly around the mound surface. The chimney is also revealed not so much as a cylindrical chimney, but as a large complex space deep within the mound. As we span the transition from mound to nest, we see how the nest's morphology is strongly differentiated from the mound's. This type of differentiation is not found in more primitive mound-building termites. Let's watch the video again. When all the photographs are digitized, they can be put together to reconstruct the entire 3D structure of the mound in a computer model, as shown here in this animation. This is a fairly crude representation, resolved at only 10 centimeters vertical resolution. However, the actual resolution is much finer, to the millimeter scale, as shown here. It is the most detailed picture of a termite mound ever made.